Hello, everybody. We are restarting the Space Habitat event. Today is November 10th, 2023. In this time, we will have the presentation of Jerry Stone. Jerry, a little bit about the curriculum. Jerry is a freelancer space presenter, presenting lectures and talks during the last 50 years. Being recognized as a space expert and also a fellow on British Interplanetary Society and also Royal Astronomical Society. He's also a author, have written 2 books and being the consultant on several others. Operates the channel Spaceflight UK, which also offers space workshops for schools, youth groups, and also team building exercise for companies. He'll be doing a presentation about the development of the Island Zero. Jerry, thanks so much for your interest to be part of the Space Habitat event. And you are welcome to present your words and also share your knowledge and your presentation. Thanks so much.
Okay, thank you very much indeed. Let me just switch the that and okay, you should be able to see my test card there, which, as you can see, features me in the middle. Can everyone see that, first of all? Yeah, okay. Okay, so as being said, I'm a freelance space presenter, and I've been giving space talks since my very first one when I was back at school over 50 years ago. So this is Professor Gerard O'Neill, who was at Princeton University. And in the autumn of 1969, he put a question to a group of new students. This was intended to be the first of a number of questions that they would discuss during their time. But they never got on to the second question. So his first question was, is a planetary surface the best place for an expanding technological civilization? And the answer seemed obvious, but they went off and did their research and they came back with something unexpected. The answer was no. Not on the Earth, not on the Moon, not on Mars or anywhere else with a solid surface. And the reason for that was that for 50% of the time, on average, you would lose the sun. Whereas out in free space, you could have the sun continuously and you can transfer that into electrical power. You could also concentrate sunlight to produce 5,000 degrees, enough to process pretty well all materials. So they did some further work to come up with a design for a habitat that could be constructed out in free space. Well, one question is, where would it be? So if that's the Earth and there's the Moon and the Moon's orbit, then Joseph Lagrange, back in 1772, came up with calculations that showed where the gravitational energy of the Earth and Moon, or in fact any other 2 planetary bodies, would effectively cancel out. So if you draw a line through the Earth and Moon, then the first of these points, Lagrange 1, is between the Earth and the Moon. And L2 is on the other side of it. Now, normally you would expect something closer than the Moon to orbit faster, and something further away would orbit slower. But the gravitational pull of both bodies, as I said, would cancel out. And so objects at the L1 or L2 points would orbit the Earth in the same amount of time as the Moon itself. There's also L3 over the other side of the Moon's orbit, which is frankly not a lot of use to us. But these 3 points are unstable. If you start to move away from them, you will continue to do so. So you will need onboard station keeping fuel to burn to keep you in position. But there are 2 other points, 60 degrees in front of the Moon in its orbit and 60 degrees behind it. And these are stable. So you don't actually have to be at the L4 or L5 points, but if you orbit those points, if you do start to move away, the gravity of the Earth and Moon will bring you back. And actually, the fact that you are orbiting the point rather than being precisely at the point is a benefit, because you can have a number of structures along the path of that orbital trajectory. So eventually 3 different designs were produced. Well, actually a number of designs, but the 3 most useful were a sphere, a torus, and a cylinder. So this is the spherical design known as a Bernal sphere, after the person who originally came up with this in the early 20th century. The sphere in the center is the actual habitat in which the population will live. And before and after it, there are a number of variously oriented mirrors, which will produce a flow of sunshine through the ring windows to the interior of the sphere. Along the axis, in front and behind it, are a number of rings, which is where the agriculture is carried out. And at the very front and very back are manufacturing facilities. And you can see right at the front, there's a parabolic dish which can focus the sunlight to provide as much heat as we want. There are also 2 sets of radiators to get rid of waste heat. So this is the second design, a torus, and in fact 2 versions of this were done. One also the same population as the sphere, which is 10,000 people, and a larger version which could hold 100,000 people. So these were known, depending on the scale, as Island 1 or Island 2. And then there's Island 3, and these are the big ones. So Island 1 sphere is only a bit under 500 meters in diameter. These ones, these cylinders, put as twin cylinders, so they would counter-rotate, so there would be no overall torque, and they'd be nice and steady. But these are 4 miles in diameter and 20 miles long, and could hold over 1 million people. So each cylinder has 3 land areas, and in between those are the window areas, and the sunlight is bounced off those angled mirrors through the windows to the land opposite. Looking down the axis of one of the cylinders, you can see how it's landscaped, and you could have lakes, rivers, though they probably need to be having pumps to move the water around. But there's be fields and areas where buildings would be placed. So coming back to the Island One design, if we look through one of the windows, we can see inside of a similar kind of setup as we saw for Island 3. The large white ring towards the upper part of the picture is the window, one of the two windows through which sunlight is transferred from the mirrors. Now, as you can see, we would take earth, trees and plants and certain animals and insects and birds. Now, we couldn't take all of the different types of fauna that we have on Earth. We just wouldn't have the suitable meteorological conditions for them all to survive. And we'd also have to be very careful about which we did take, because we wouldn't want one to flourish in an uncontrolled management, such as the rabbits that were taken to Australia. We would certainly take bees so we could produce honey, but we might leave wasps behind so we can have our picnics, as shown at the bottom of the picture, in safety. However, having said that, there are reasons why we might want to include wasps. So we'll have to go into this in a lot more detail. We'll need ecological research on this. Now, we wouldn't construct this out of material taken from Earth because of the huge cost of launching. But we know from the Apollo project the composition of lunar soil and rocks in various locations on the moon. As you can see, there's a huge amount of oxygen, which is good for our inhabitants to breathe. There's silicon, so we can make windows, iron, aluminium, magnesium, and other items, including a large quantity of titanium. Typically, on the if you compare it to what's on the Earth, there's over 5 times as much titanium on the moon. So the moon also has 2 other advantages. Firstly, because there's no atmosphere to slow down any vehicles being launched from the moon. And also we have sunlight to provide power. So together we can use those to build an electromagnetic launcher. So we wouldn't actually need to burn any fuel to get the material off the moon. The other thing is we would not need to mine the moon. We could get the 500,000 tons needed for the structure by simply using a bulldozer and scraping the surface of the moon. An area 200 meters square and about 7 meters deep would provide sufficient material just by using one bulldozer over the construction time period down to about a level of 7 meters. And obviously it would be an electric powered one, so it would use solar power, only available half the time, of course, but that would be quite adequate. So Gerard O'Neill fitted to the design 2 restrictions. One was cost. It had to be costing no more than Project Apollo, or the equivalent of it, so that nobody could say, well, it's a nice idea, but we can't afford hundreds of zillions of dollars. The other thing was it was restricted to the technology available at the time. So nobody could say, well, it's a nice idea, but it depends on this and this and this that we haven't invented. So with the design produced in the mid-70s, if we started that and allowed some time to get the project underway, then this structure could have been built in the 1980s with 10,000 people living and working on there. So I thought in 2013, so just about 40 years after the original designs were produced, that we have had great improvements in technology and materials. We had some materials that were much better than we had back then. We had new alloys. We also had materials which didn't exist back in the mid-70s. And we also had new techniques, constructing materials by 3D processing, for example. So I proposed to the British Interplanetary Society that we should set up a project to investigate this, to advance the Island 1 design and to produce a report on that. So I called it the Space Project. This is my sense of humor. Study Project Advancing Colony Engineering. Although I have to say, I actually prefer the word settlement rather than colony. So we have Island 1, Island 2, and Island 3. But before building Island 1, or in order to build Island 1, we need to extract the raw material from the moon, process that material to extract the various elements, to manufacture from those elements the parts that we'd need, so windows, beams, panels, and so forth, and to produce the assembly facilities to put all this together. Well, before doing any of that, we would need to provide facilities for the teams. We would need offices, workshops, and living quarters, because they wouldn't be going up and down from Earth continually. So we would need a relatively small scale unit in which the people would live and be the base from which they would work. And having gone outwards, Island 1, 2, and 3, we went inwards and called this Island 0. It would rotate to provide simulated gravity. It would be made of modular components, perhaps 4 or 5 different types of modular components. So it would cut down the production cost. They would grow a lot of their own food on board rather than have to have it sent up from the Earth. And they would also, in this initial unit, do much of the manufacturing facilities to produce the facilities that would be needed in the for the main Island 1, but obviously on a much smaller scale, because at this stage we'd only be testing and proving these activities. So we assumed the main modules would be 15 meters long by 4.8 meters in diameter, and they would be inflatable. And possibly, when we first started this, launched from the Earth's surface by the Skylon space plane, which is being developed by the UK's Reaction Engines company. Now, what makes this so different from anything else that has ever been launched before is that this is a single stage to orbit launcher. Now, up until now, we've needed at least 2 stages to get to orbit. The first stage carries most of the fuel that will get off the surface of the Earth, and then that stage will be dropped away when the fuel has been used, and the upper stage will then continue on from there, having reached a good height and velocity. Now, the reason you can't normally do that with one stage is because you have to take so much fuel to get you off the ground. But Skylon works in a different way. First of all, it takes off and lands horizontally. And the two engines at the edge of the two wings operate in a completely different way. They start off as jet engines. So they are able to get the craft up to a speed and height by taking in air from the front. And it does two things. First of all, it actually uses that air to run as jet engines. It also extracts the oxygen from the air and chills it down within a fraction of a second. Now, this is the main technology that's needed, and this has been developed and tested, and also tested by other organizations, including the European Space Agency, and it has passed every single test. Initially, it would be operated in unmanned mode, but it would be possible to have a crew on board as well. So if we take the modules and compress them, because they would be inflatable, like the ones already produced by Bigelow Aerospace. And at that size, the red outline is the Skylon payload bay, and you'd be able to fit 4 units. So you could launch 4 of what we assumed would be 8 modules in a finished Island 0. And we assumed initially that, of course, they'd be arranged in a rotating ring like this. However, if each one's 15 meters long, then the overall diameter would be about 50 meters. So then I did some calculations on what effect of gravity we would gain by rotating this at different levels. And if we look at the first column at 25 meters radius, then with 1 RPM, you'd still be practically weightless. And even at 3 RPM, you'd only get 1/3 of a G. And that really doesn't help us. We're looking for something around 1 G. So if you see going down from 150 meters at 2.5 RPM or 175 at 2.25 RPM. And we would want the G value to be pretty close to 1 G. So they wouldn't have to do 2 hours of exercise every single day as they do on the International Space Station. Now, when we started the project, and we got a number of volunteers together to work on this, I asked them a few questions. In fact, what I said is, the first thing I want you to do is not to say, oh, we should do this and this. I want you to come up with questions that would need to be answered in order to have a suitable design. And I started off by asking them a question which I didn't expect to get an answer to, which is, it's always assumed that these large habitats will rotate to provide 1 G. Do we actually need 1 G? If we rotated to provide 0.9 or 0.8 G or even less, there would be less stress on the structure, so less material would be needed to construct it. There'd also be less stress on the inhabitants, on their cardiovascular system, on their muscular system, their skeletal construction. So that means that over a period, a long period, the inhabitants would be taller than if they lived permanently on Earth. And we'd actually need to take that into account in the architecture taller windows, taller doors and ceilings. But the big question is, of course, how low can the simulated gravity be before it becomes a problem rather than a benefit? And the answer to that is nobody knows, because we have never done it. So the first thing we need to do is produce a small version of an Island 0, so that we can carry out the medical research to get the answer to this. And that will affect the design of an Island 0 and larger units. So with a radius of 200 meters, which was about the radius of the Island 1, then at 2 RPM, which would be quite tolerable, we'd have just under 1G. But this is meant to be a low-cost construction. And with a radius of 200 meters, we'd need 84 units in a continuous ring, which is certainly not low cost. But instead of having them in a continuous ring like this, how about if they were set radially? We could then extend them out to 200-meter radius and add an outer ring to connect them. Now, those connectors that go to the center, you wouldn't want to have ladders all the way down there, because going down wouldn't be too bad. Going up against gravity, even though it gets less as you get towards the center, would sort of be okay for people. But if you want to dock vehicles along the center hub and then transfer material out to the modules, then you need ropes or other things at least, because you couldn't just let them drop, because they'd be reaching 0.9 G at the outer end. So we came up with this. First of all, the units would be divided into various floors. That grey circle is where the connecting ring would be joined on. And instead of having vertical connections between the floors, we assumed there would be essentially a circular spiral staircase fitted to the inside of the outer wall. So the habitable volume of just one of these items would be 270 meters cubed. So 8 units would be 2100 meters cubed, and the Destiny unit, which is the largest individual unit on the International Space Station, to the same scale, as you can see, is much, much smaller. The total habitable volume on the International Space Station is less than half of what an Island 0 would be. So to get to the outer modules from the center, we've suggested a curved set of modules that you'd be able to go down. And the reason for having them curved is so that by the time you get to the end of them, you would be pretty much at the simulated gravity level of those outer modules. So that we'd have 4 of these. Another way of doing it is to turn the modules through 90 degrees. So instead of having 5 small areas, there would be 2 large ones, which would be actually more efficient. So the unit would look like this with 8 modules, although initially we'd probably only have 4 modules, because we wouldn't need that amount of room for everything. And Adrian Mann, one of our project members, came up with this lovely CGI image showing the unit with several modules along the central hub, and also some solar panels. And at the top, there is a Skylon docked to the unit. And this is his animation of it, which I think is absolutely terrific. So we have a title, the Space Project, and we have a logo. However, when Gerard O'Neill wrote his book about this called The High Frontier, and he listed various benefits of it, he mentioned that because we're getting 95% of the material from space, and we'll also use space-sourced material to carry out construction. And because of the availability of this material, that countries would no longer need to have resource wars to get material from other countries. So going into space could mean that we could do away with war. And it struck me then that if you rotate the logo, that's exactly what it tells us. So we also have a call from Blade Runner.
The chance to begin again in the golden land of opportunity and adventure.
So benefits of doing this, I mean, that is obviously the main question. Why bother? Okay. First of all, a lot of heavy construction, which is currently done on the Earth, can be moved out into space. We will source materials from the moon instead of mining the Earth. We will use power from the sun instead of burning fuels such as coal, oil, and so on. We wouldn't need to spend billions producing fusion power. Right. And doing all this work off the surface of the Earth means we would reduce pollution. And also we would reduce our carbon dioxide output. So it could make the Earth a much better place in the future. And as I said, it would reduce international resource claims. So a while ago, Frank White produced a book called The Overview Effect, and it contains a most fantastic statement, which I quote as often as I can. War and space exploration may be mutually exclusive, because if one occurs on a massive scale, the other probably will not. Now, as it happens, yesterday, I gave a presentation to the Kepler Space Institute, which is an online university. And I was invited to do so by another member of the Space Renaissance Initiative. And when I got to asking her questions about the presentation, I said, so what sort of size audience are you expecting? And she said, perhaps just about 6 of us. There'll be 3 students and 3 lecturers. And she gave me a list of the names. And one of them was Frank White. And I wrote back and I said, well, it would be really terrific to have the author of the overview effect in the audience. That would have been really nice. And she wrote back, he said, well, actually, it is. So yesterday I gave Frank White a presentation about Island Zero. So I have a summary of the space project and the Island Zero idea. In fact, I have recently enlarged this because obviously more work needs to be done on the definition of Island Zero and coming up with a suitable design for that. And that really needs to be done by people who do this sort of thing for a living. So I've suggested that the European Space Agency carry out a phase A feasibility study. And so I've enlarged the information in this and added in that proposal. And hopefully that will go to ESA perhaps at the beginning of 2024. And I'm quite happy to send copies of that to any of you. If you want to just write to me, jerry.stone2001@gmail.com, and I'll be happy to do that. Okay, I'm going to stop there. Well, I thought I was going to stop there.
Okay, Jerry, thanks so much for the wonderful presentation. Also, we are open to questions. If Aaron, Mario, and Thais,
Thank you.
You are welcome to comments and contributions.
Yeah, by all means, if you want to unmute yourself. No?
Yeah, I consider very inspiring. Something that I was thinking, how to bring the concept of Island Zero to kids, how they can motivate themselves to imagine the different concepts about the space stations too, because this is the imagination is accessible to everyone. There is no cost.
Obviously, there are opportunities with STEM in school: science, technology, engineering, mathematics, and you could start with a 4-module Island Zero, and then have designs that grow from that. And one of the questions that we want the feasibility study to look at is what kind of activities could be done on board Island Zero that would be useful for the future. So, I mean, something that we could do is, so let's say that we have 4 initial modules, and it is, say, rotating to produce 0.9 G. If you have other modules that you add further outwards, then you could increase that to 1 G. If they were closer to the hub, you'd have 0.8 G and perhaps even 0.7. So you could have people living at a particular level, say for 3 months, carrying out a lot of medical research, and then have them move to another level and do the same research. So it's the same research on the same subjects, and you could compare the results. So that would be very useful indeed. And as I said, it would also, they would also carry out the work to produce facilities to extract from the raw materials. So to bring out the oxygen and silicon and so forth, and also do small scale versions of facilities that would then make the windows and the beams and panels and so forth. And the original plans for Island 1 envisaged it requiring a construction force of about 2,000 people. But our, as I said, our technology has improved. Our computing power is several orders of magnitude beyond what it was originally. And we also have robotic technology, which is far more advanced than it ever was. And I'd be surprised if we actually need more than 500 people to construct an Island 1, which is actually very important because the biggest cost in any space project is the cost of the people involved. So I'm not thinking about the 3 people on each of the Apollo missions, but the 400,000 people that were responsible for it. If we can reduce the personnel cost by 75%, it means not only could we do this more effectively now, we could also do it a lot cheaper. There we go.
Which logistics system do you consider to transport the components for space?
Well, okay, so I mean, again, 40 years ago, pretty well all space activity was carried out on behalf of government agencies, and that is no longer the case. And in fact, Jeff Bezos and Elon Musk together could fund this entirely by themselves. And they also have, I mean, we don't have Skylon yet, but they have the vehicles that could put up the initial modules to construct an Island 0 just by themselves without anyone else. But I would expect, and I would like to see Island 0 being produced by a number of companies working together as a consortium. That to me makes the most sense, because when we get to building an Island 1, that will not be built or organized by or on behalf of government agencies. We would want it also to be run. I mean, a population of 10,000, that's equivalent to a regular town. So it would need to have its own means of government. And so part of continuing investigation is how should that be arranged?
Okay, thanks. Mario has a question.
Yes.
Can you hear me?
Go ahead. Yes.
I would like to congratulate you on this exciting presentation. And I don't know if you are aware of the plans of orbital assembly, also known as above space, regarding a rotating station. I wanted to ask you what you think about it.
I'm not sure if I know of that one. I know that there are a number of different designs of space habitats, and something that I suggested yesterday to the Kepler Space Institute is that it would be really good to have a meeting of the various organizations who have come up with designs and compare them. And one point of possibly doing that is the IAC conference next year, which is going to be in Milan. So that seems to be a useful type of location for something like this. In fact, perhaps we could have a session, perhaps a day session of the IAC devoted to this. And we would want anyone who is interested to be able to come to that.
Yes, Mario is from Italy. It's close to
Yes.
Milan.
Well, there you go. Yes, yeah. Of course, I should have asked. So
Yes,
how
I
far are
will
you?
be there.
So how far are you from Milan?
I'm located in South Italy.
Okay.
About 900 kilometers, but
Yeah, not that far
it's
to
not
go, really.
that far. Yeah.
Very good.
It will be a good occasion to meet you in person.
Yes, thank you.
And Jerry, how much time do you believe is necessary to be feasible? Like maybe 20 years or
What,
30
for
years?
Island Zero?
Yeah.
Okay. So I'm assuming up to 1 year for the feasibility study. Then I think perhaps just a year for the design to be finalized from that. Perhaps 2 years for constructing the modules. And after that, because they will have to be launched from Earth, and that will have to be paid for. I would think, I mean, because it's not just the modules, but the interior, all of the equipment, obviously the environmental control system and so forth would also have to be manufactured and launched. And we wouldn't, well, I'm not sure how much we'd need to put up before it could be used for initial research. Obviously, the smallest unit would just be 2 modules, but it would probably be better stable if there were 4 as a minimum. And we need calculations on how long the central hub would need to be, because if it was effectively flat, then as well as rotating that way, it may wobble around an axis as well. So we need stability for that. And that may have to be done by onboard rocketry. But if it can be done by extending the central hub, if that would make it more stable, then that would be very useful. And also give some weightless research areas as well.
Okay, thanks. Okay, more questions? No, okay. Okay, Jerry, you have like some 2 or 3 minutes to some last words to conclude and how to inspire more people to be interested about imagine the space exploration. You are very welcome to conclude.
Well, inspiring school pupils, it would be great to give them a short presentation like this and to come up with ideas from which they might produce designs for other Island Zero modules, and to have them think about what would be needed beyond the main structure. So obviously for people living on there doing this research for a long period, I mean, it is medical research that we need most. So obviously we'd need at least 2 doctors on board. But what other type of people would we want there? We obviously want engineers. and people who could actually take material from sent from the moon and break it down into its constituent parts. So people with that kind of knowledge. So, and also, as I said, there's a question of how it would be governed. So with Island Zero, and I have to say, I'm assuming that all of the organizations involved with that would probably come from America and Europe. So the question of whose government they should come under, and I imagine the answer to that would be pretty much similar to how they run the International Space Station, that the people on board operate under their own government's restrictions. Okay, so I can see in the chat from Aaron, I have a question. What do you think about the 3D printing technology for construct the bases on the surface of the moon? Will it be viable? Well, I know that there are already plans for producing moon bases by 3D printing. And this is being developed to a much greater degree now than when it was first introduced. The fact that, as I said, that you don't actually have to mine the moon to get the raw material. Obviously, you need facilities to extract the various elements and compounds from the raw material. But after that, though, it's been suggested that you could have simply not buckets, but large containers of each type of material being fed into a 3D printer to produce the output. Not sure. I meant to look this up, actually. I'm not sure if you can 3D print glass panes, but though what I had assumed was that they would not be produced out at the L5 point, but you would produce the glass panels, windows, on the moon. The reason for that is the way that we produce large glass panels on Earth is to melt the silicon and have it floated on a layer of liquid tin. And that makes it absolutely flat and smooth. So you would need that to be done under gravity. And it makes sense to do that where you're extracting the silicon to begin with.
Okay. Okay, Jerry, thanks so much for your contribution. And
Sorry, just one other thing I've thought of.
okay.
One thing that you would produce out at L5 under weightless conditions would be to extract metals and inject gas into it to produce foam metals. Now, obviously, you cannot do that under gravity, but you could then produce beams which would be lighter, and we need more research into this as well to know what percentage of gas per cubic volume is needed. But you could have beams which would be just as strong if they were solid, but using a lot less material. So again, that's just an example of the number of different areas of research that needs to be carried out. Okay.
Okay, thanks so much, Jerry. I'm concluding the recording.